boson, I'm going to use the fact that you've very well filled the front half of the room. That's very good. You haven't all sat up in the back rows. Excellent on that. Some years ago at Bristol University, I analysed the exam marks of my students compared to where they sat. Now, you have to be very brave to sit in the front row because you might get picked on, and I am going to pick on a student later. But if you sit in the front half, it will be much more immediate. What I did was I compared the marks of the people in the front half of the room to the people in the back half of the room. And of course some did better than others, but on average the people in the front half got 10% more than the people in the rear half. That's a whole degree class. So when you go to university, as I'm sure most of you will, whatever you're going to study, do try and sit in the front half, because it will be much more immediate. The information comes from the front, either from the speaker or on the screen, and I think what happens is it gets filtered out by the people in the front half, and so very little reaches the people in the back. You may have other explanations, I don't know. But anyway, congratulations that you didn't all sit right at the back, although there is still the opportunity for some of you to come further forward, so I don't need to raise my voice quite as much, if you'd like to do that. Anyway, yes, this talk has two titles. It's the same talk, I offer how the Higgs boson was discovered, or I like to say how I found the Higgs boson, but of course I had 3,000 colleagues on our experiment, there were another 3,000 on the other experiment, Atlas, and of course the whole CERN's machine, the whole staff, operating the accelerators, the computers, everything to make it all work. So about 10,000 people altogether were involved in the discovery of the Higgs boson. So I'm just a very small part of the machinery. But it still allows me to say it, because my name is on the scientific paper that we published in July 2012 with the discovery of the Higgs boson. I can say I discovered the Higgs boson. So yes, actually, I'm retired now, I have an honorary position at the University of Bristol, and I've been spending my gap year in Australia working at the University of New South Wales. This is me standing in front of part of the CMS experiment, which I'm going to tell you more about later, when it was being constructed. And this is where the Large Hadron Collider, LHC, is located, across the border between France and Switzerland. So I always like to say that protons, which go round 11,000 times a second, are imported and exported 22,000 times a second. Fortunately, no duty to be paid as they cross the frontier. And I've forgotten to pick up the clicker, which will allow me to go to the next slide. Let me do that now. Right, so yes, that's what it looks like in more detail. Is it possible to turn off the front lights? All or none? Okay. I think we probably want to leave them all on, or else I might fall asleep in the dark. Of course, if this were America, you'd just shoot out the front. So, there we are. The Large Hadron Collider. The Jura Mountains on the left, the airport you can see on the right, and Lake Geneva in the top. And this shows you not only the Large Hadron Collider, 27 kilometers round, but also some of the other accelerators that feed particles into accelerating particles. Now, sometimes when people fly into Geneva Airport, they look out of the window and they say, I can't see this circle out of the window. Well, of course, that's because the accelerator, the collider, is 100 meters underground. It's in a tunnel 100 meters underground. So there's essentially no radiation at the surface. CERN couldn't possibly afford all of that land. We only own the land at 8 sites round the ring. Everything else is 100 meters underground, so that housing, agriculture, forestry can carry on as normal on the surface. So, what am I going to talk about? I'm going to give you a little background of the Standard Model. Many of you, most of you perhaps, have already studied the Standard Model, so I hope this will just be a review for you. I'm talking about the elementary particles and the forces between them. The forces are, of course, just as important as the particles, because without those forces, they wouldn't stick together to make atoms and molecules, stars and planets, trees and people. So the forces are just as important. Then the motivation for the Higgs boson. Why do we need the Higgs boson? How do we go about making it? And how do we recognize it when we have? So, Standard Model. I think it's on 2 slides. First slide is the matter particles. Even if you haven't studied the Standard Model, looking at the top left, you'll know that matter is made of atoms. And we've known since 1911, Rutherford explaining the experiments of Geiger and Marsden in terms of a very, very small but very, very heavy nucleus at the centre of every atom. It's much, much smaller than shown on the picture. It's like 1/100,000th the size of the atom. If it was drawn to scale there, you wouldn't be able to see it. It would just be a pinhead. But it has almost all the mass of the atom, 99.5% or more of the mass of the atom in the nucleus. And since the 1930s, we've known that the nucleus is made of particles we call protons and neutrons. Protons with positive charge, neutrons electrically neutral. And since the 1960s and 70s, we've known that the protons and neutrons in turn are made of even smaller particles that we call quarks. Unless you come from the United States of America, in which they're made of smaller particles called quarks. There seems to be this difference on the 2 sides of the Atlantic of how to pronounce it. But I say quarks. They come in 2 sorts. They have peculiar properties. They have fractional electric charge. The up quark has charge plus 2/3 the elementary charge, E, and the down quark has minus 1/3 of the elementary charge. So that if you take 2 up quarks, plus 2/3, and 1 down quark, minus 1/3, that comes to 3/3 of E, or just plus E, the charge of the proton. On the other hand, if you take 1 up quark and 2 down quarks, that comes to 0, the neutron is electrically neutral. And the interesting thing is you only need the particles on that top row to describe all ordinary matter in the universe today. Up and down quarks in protons and neutrons in the nucleus, adding electrons to make atoms and molecules. We even have the electron neutrino, which is a very, very light, electrically neutral particle that's emitted along with electrons in radioactive beta decay, for example. Also in the reactions that keep the sun shining and other stars. The neutrinos are emitted along with the energy that the fusion process produces, and we can actually detect those neutrinos from the sun, or some of them. That's another story on Earth. But during the last century, we found more examples of these particles, heavier than the particles in the top row, and unstable. In a very short space of time, they break up into the particles in the top row. The first one in the 1930s was the muon, which is just like the electron, same electric charge, same angular momentum or spin, but 206 times heavier. It has its own neutrino, and we found heavier versions of the up and the down quarks. We call them charm and strange. Charm is just like the up quark, but heavier. Strange is just like the down quark, but heavier. And as if that wasn't enough, then in the 70s, 80s and 90s we found yet another set of particles, starting with the tau, again just like the electron, same electric charge but 3,000 times heavier, with its own neutrino, and 2 more quarks which were actually predicted before they were found. The authors of the paper that made the prediction called them truth and beauty, so that it went strange, charm, beauty, truth in order of mass. Well, we've kept those initials, T and B, but nowadays we refer to them, well, usually we do just refer to them by the initials, T and B, but we call them top and bottom by analogy with up and down. I think it's a shame that you do sometimes hear people talking about beauty quarks, but almost never about truth quarks. I think it's a shame to call it top, because if somebody says we've discovered the top quark, and that's what happened at Fermilab near Chicago in the 1990s, you think, well, top, that's it, there aren't any more. But actually that's an open question. Could there be even more particles, even heavier, to make another row or rows in this time? Now we call these the matter particles, and every one of them has an antimatter counterpart. Same mass, but opposite electric charge. A sort of mirror image particle. So the matter particles, and for every one of them there's an antimatter particle as well. So that's the standard model of matter particles. Then come the forces, and physicists have discovered 4 forces in nature. The most important one on the everyday scale, of course, is gravity. Gravity is what's holding me to the floor. Every particle in my body is attracted to every particle in the Earth. But on the elementary particle scale at present, it's totally negligible. The gravity force between 2 protons or between 2 electrons is completely negligible, so we don't need to bother with that. That's why I put it in brackets. Electromagnetism is important because most of the particles on the previous slide were electrically charged, so they attract and repel each other, and as they move, they are electric currents, so there are also magnetic forces between them. Those first 2 forces, gravity and electromagnetism, both fall off with distance, as I'm sure you know, 1 over r squared, inverse square law of forces, but they're still there at large distances. Gravity operates in the solar system, in the galaxy, even between galaxies, gravity forces. Electromagnetism, the Earth has a magnetic field, the Sun has a magnetic field, there are magnetic fields in the galaxy. So they are very long-range forces. But the other 2 only exist on the scale of the nucleus, or smaller. One is a lot stronger than the other, about 10,000 times stronger, so we call them the strong nuclear force and the weak nuclear force. The strong force is the one that holds the quarks together in the protons and neutrons and other strongly interacting particles. It glues them together, if you like, in the protons and neutrons, and a little bit leaks out, a little bit of the force leaks out to hold the protons and neutrons together in the nucleus. The weak nuclear force is the one that's responsible for radioactive beta decay and the reactions in stars that I mentioned. And every one of them has carrier particles. Let's forget about gravity for the moment, but electromagnetism is carried by the particle called the photon, and we use the symbol gamma from gamma rays for that. The strong nuclear force, which glues the quarks together in the protons and neutrons, is carried by 8 particles called gluons. Silly name, but it certainly describes what they do. And the weak force has both charged carrier particles and neutral carrier particles. The charged ones, W plus and W minus, and the Z, which is electrically neutral. So there you are, 2 transparencies covering the whole of the standard model of particles. Now, those particles that are exchanged to produce the forces, let's have a little look at the mechanism of how that works. And there's a diagram there of 2 young women in boats exchanging a heavy medicine ball between them. Let's see if we can reproduce that. If I have a volunteer, please. It doesn't have to be from the front row, but if I don't get a volunteer, then I pick someone. Good. What's your name? Jonathan, right. If you stand there, Jonathan, and I will throw the ball to you, and as I throw it, I will recoil, conservation of momentum. And as you catch it, you will recoil by conservation of momentum. And if we continue throwing it to and fro, exchanging the particle between us, we will move apart, we will get repulsion by exchanging the particle. Good? Now come a little bit closer. I'm sure some of you will be asking yourselves, well, how's he going to explain repulsion in that way? If you come here and stand with your back to me, and I bring my other piece of high-tech equipment, I told you I've been working in Australia, so I have a boomerang. On health and safety grounds, risk assessment, I'm not actually going to throw it, but you have to imagine that I stand here and I throw it in that direction. Once again, I will recoil as I throw, and it will go zip, 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 zip round, and Jonathan will catch it and recoil towards me as he catches it. Then he throws it back, he recoils, it goes zip, 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 and I catch it, and I recoil. So we can produce an attractive force as well as a repulsive force between us. Thank you very much, Jonathan. Now, I know you're all thinking, he's gone crazy. Particles aren't boomerangs. I have to tell you, they're not tennis balls either. You probably all know that particles sometimes behave as particles, sometimes behave as waves. We should actually call our subject not elementary particle physics, but elementary wavical physics. But people would laugh at us if we did that. So what we do is we redefine the word particle to mean these peculiar things that have some particle-like properties and some wave-like properties. So, how do we do that with waves? What I want you to imagine is that the room is filled with water to about halfway up, and perhaps there's a plastic cup resting on one of the chairs up there. This place is filled with water. What I do is I make a big splash here, and waves ripple out, and they bounce off the walls, and they come together, and they interfere, and perhaps they interfere constructively and knock the plastic cup off the wall. But you can't say how the energy got from here to there, because it took every possible path, bounced off all the walls. It's not like the tennis ball, you can follow the tennis ball in one direction. It's not like the boomerang, you can follow the boomerang. With waves, the energy takes every possible path from one event to another. So, if we're going to do calculations of what's the probability of a particle interaction or something like that, it's quite a difficult job, because we've got to add together all these possible routes from one place to another that the particle or the particle wave might have taken. And adding lots and lots of things together, I'm sure you'll soon realise, involves integration. Right? We've got to integrate over all the variables, and of course it's not just a two-dimensional thing like this room. Space is three-dimensional. We've got to follow those waves in every direction. So there are the particles that you exchange forces. So let's try looking at that. I'm going to skip that one. Here is a diagram representing two particles scattering from each other. Normally, you're told to plot time along the horizontal axis as the independent variable, and other things on the vertical axis as the dependent variable. But I'm afraid in theoretical physics they do it the other way around. They plot space along the horizontal axis and time along the vertical axis. So at a given time, low down on the picture, you have a solid line. That's a matter particle, could be an electron, and a wiggly line which represents a force particle, could be a photon. So the photon comes and interacts with the force particle. It gives energy to it. One of the slides I just omitted says you've got to conserve matter particles. You always have to have the same number of matter particles at the end as at the beginning. Just like chemistry, I expect some of you know, you have to balance your equations. Same number of hydrogen atoms on the left and on the right. Same number of chlorine atoms on the left and on the right. We're allowed one extra rule though, and that is you can make antiparticles along with particles. So if you make extra particles, you have to have antiparticles to balance them. But the total number of particles minus antiparticles is conserved for the matter particles, but not for the force particles. So that photon is absorbed, the electron moves upwards in time and to the right in space, and a little bit later it emits a photon. So there's a photon travels on the left and the particle travels to the right. So that's a Feynman diagram which represents that process. That's the thing that you have to integrate over all possible positions in space and time. But unfortunately, bad enough as that is, that's not the only thing that can happen. Oh, by the way, there's a picture of Richard Feynman who invented these diagrams as a means of keeping track of your integrations, of how many calculations you need to do. On the right is a more complicated Feynman diagram, where particles appear and disappear, scattered, and so on. So you have to take account of that a photon in your picture could break up into an electron and a positron, and a bit later they recombine to produce another photon. So your calculations are getting more and more and more complicated. You have to do more and more complicated integrals. Fortunately, in the case of electrons and photons, what we call electrodynamics, quantum electrodynamics, fortunately, those series converge. It doesn't get worse and worse as you go on. But we need to sum all of these possibilities in each order. As I said, it does converge in the case of charged particles and photons. But if we want to do it with the weak interaction, if we want to be able to do these calculations to see whether what's the probability of particles scattering from each other, the big question is, will the process converge? And the big difference is, whereas photons have zero rest mass, that's what makes the recipe work, that's what allows the series to converge. When people first started doing it with W and Z bosons, they ran into difficulties. The series did not converge. In the technical jargon, it is not renormalizable. So it just got more and more complicated, bigger and bigger infinities every order that you try to do your sum with. So life would be a lot easier if the W and the Z bosons, and indeed the heavy particles, the matter particles, all had zero mass. But that would be a very peculiar universe, because anything with zero rest mass always travels at the speed of light. So if quarks and electrons and everything had zero mass, they would never come together. They would never slow down and come together. They would always zip about the universe with the speed of light. So it would be a rather boring universe. So how do we get over this problem? Well, so the question is, why is there such a range of particle masses? I didn't tell you that the top quark is this weight of 175 protons. I did mention the muon, 206 times the mass of the electron, the tau, 3,000 times. So why is there such a range of particle masses? And as I've just been trying to explain, why do they have mass at all? Because that makes life difficult for our theoretical problems. And nearly 50 years ago, a group of 6 physicists invented a mechanism to overcome this. What they said was, well, yes, the particles do have zero mass left to themselves, but as they travel through space, what we think of as empty space, that space is filled with a field. Not one of the fields we've been looking at, gravity, electromagnetism, and so on, but a special mass-generating field. As the particles interact with this field, that slows them down, that gives them inertia, that gives them mass. We actually call the field after 3 of these physicists these days, Brock, Englert, and Higgs. Brock, unfortunately, is dead. Englert and Higgs, as I'm sure you know, got the Nobel Prize for this prediction last year, autumn last year. But there were 6 people, at least, involved in developing the theory. So, what we think of as empty space is filled with this BEH, Brock, Englert, Higgs field, and the more strongly the particles interact with that, the more they're slowed down, the more mass they have. So clearly a top quark interacts very strongly with it, and the lighter particles interact less so. An analogy, I used to say, well, it's rather like moving through treacle. If you try to move your spoon through treacle, it's not just the mass of the spoon that you're moving, but this is not a very good example because it's dissipative. You lose energy as you do that. Now that's not what happens with the particles in space. They're just given mass, but they don't lose energy. A better example, but it may not even be in the A-level syllabus these days, so it may not work for you, is it's like light going through a transparent material. As I'm sure you know, in a vacuum, light travels at a speed of 299,792,456 meters per second. I'm sure you all knew that. 300 million meters per second for those that like to round it off. But when it goes through a material like glass or like water, it slows down. and we measure the amount that it slows down by the refractive index. Now, is refractive index in the syllabus these days? Probably not. Have any of you heard of it? Okay, good. So it slows down because the photons of light are interacting with the electrons in the material. And the more electrons there are, the more they slow down. So, for example, lead glass has a very much higher refractive index than ordinary soda glass, which is why people use lead glass for their chandeliers, because it glints more. But it's the interaction of the photons with the electrons in the material that slows them down. So that's the analogy for particles moving through empty space interacting with this BEH field, or sometimes just Higgs field for short. Now, why is it particularly named after Peter Higgs? Because he went one step further than his colleagues and said, well, if this field exists, there should be particles associated with it, just like there are particles associated with the electromagnetic field, with the weak interaction, the strong interaction, and so on. And these particles are Higgs bosons. So bosons, if you want to ask me what are bosons, it's one of the slides I skipped over to save time, but you can ask me at the end. So Higgs bosons were predicted nearly 50 years ago. The trouble is, the theory doesn't say how strongly they interact with themselves, how strongly a Higgs boson interacts with this mass-generating field, and therefore what mass it has. So over those 50 years, as we've gone to higher and higher energies, as each accelerator has been turned on, the more energy you have, the more heavy particles you can produce. E equals mc squared, energy and mass very closely related, so if you have more energy, you can make higher mass particles. So at each step in energy of our accelerators, we've wondered, oh, can we make Higgs particles? But it wasn't until the Large Hadron Collider that we actually do have enough energy to make the Higgs particles, but they are quite rare, and it took quite a while to get statistically significant evidence for these particles. Okay, that's what I've been talking about. What about the mass of the Higgs particle? E equals mc squared. If it's a very heavy particle, we need a lot of energy to do it. So back to the Large Hadron Collider, where we can collide particles together with very high energy. So let's talk a little bit about how we do that. We use not just one accelerator, but a whole chain of accelerators, each one giving a little boost to the particle. We say it's a bit like a child on a swing. You can either, the analogy at this point, it's a little bit like a multi-stage rocket. With a multi-stage rocket, each stage gives more energy to the payload, but of course, in a multi-stage rocket, each successive stage is smaller than the one before. Here, our accelerators are each larger than the one before. Here's an example, or here's a picture of the chain. The protons start in this linear accelerator, which I think you went to see last time, right? And from there, they're injected into the booster, and the proton synchrotron, which started in 1959, the super proton synchrotron from the 1970s, and then finally, the clockwise and anti-clockwise into the Large Hadron Collider. So a whole chain of accelerators, each one giving more energy to the particles. And the analogy I started was, in each accelerator, each time they come round, they're given a little kick of a few kilovolts, building up to finally 7 trillion volts in each direction in the Large Hadron Collider. And that's the analogy I started, like a child on a swing. You can either give them all the energy at once, so they probably fall off and start crying, or you give them a little push at just the right time, and that builds up the energy. And just the right time means that the push we give them is with an oscillating electric field, because we don't have any trillion-volt batteries. So we use an oscillating electric field timed as the particles go through. It's in the particles are not in a continuous stream, they're in bunches, and as each bunch goes through, they get a little kick. Hence the word synchrotron, because the accelerating field is synchronized with the particles going through. So then we collide the particles together, and that's where we can turn their kinetic energy from the accelerator into mass. But any new particle we create, for example the Higgs boson, or any of the many other types of particles we're looking for, will be very unstable, and that will break up very quickly into daughter particles, and so the energy of the mass of the parent particle will be in the kinetic energy of the smaller particles. So what we have to do is we have to identify those daughter particles, and there'll be many, many of them, measure their directions, measure their energy, work out what would have been the mass of the parent particle if they had come from a single parent particle, to understand what happened. And of course, to do that, we need plenty of computers, in fact, getting on for 100,000 PCs to analyze that data. So let's look at the accelerators. This is the Large Hadron Collider. Artist's impression. You can see the Jura Mountains on the right here, the airport and the lake on the left, and we're 100 meters underground. The particles go around clockwise and anti-clockwise in their bunches, and the bunches are timed to pass through each other at each of the 4 underground experiments. So the collisions take place only at the 4 underground experiments. We call them bunches, but that's not a really very good name for them. Each bunch contains over 100 billion protons. Getting on for 150 is our record for the moment, 150 billion protons. In a little sort of pencil-shaped thing, 7.5 centimeters long and 16 microns, 16 thousandths of a millimeter, or 1/5 of a human hair in diameter. So as they pass through each other, out of those hundreds of billions of particles, on average, we get about 30 or 40 proton-proton collisions. But as they pass through each other 40 million times a second, we get lots and lots of collisions. Unfortunately, most of the collisions are just glancing collisions, not a lot of energy exchanged. So although we have 40 times 40 million proton-proton collisions a second, we only actually make a Higgs boson about once a fortnight. They are very rare because we need head-on collisions, not just head-on collisions between 2 protons because they're composite, they're made of quarks held together with gluons. We need a head-on collision between 2 quarks, or more likely between 2 gluons, to get the energy we need to make Higgs bosons. But that's an artist's impression of what it looks like. Atlas at the top there, and CMS at the bottom are the 2 general-purpose experiments that I'll go on and describe a little bit. The other 2, ALICE and LHCb, are special-purpose experiments. ALICE is particularly interested in producing the conditions of the Big Bang in our collisions. As well as colliding protons with protons, we can collide, protons of course are the nuclei of hydrogen, the lightest atom. We can collide lead ions. Lead is the heaviest stable element. So colliding 208 protons and neutrons with 208 protons and neutrons puts a lot of energy into a very, very small space and recreates the conditions of density and pressure and temperature of the Big Bang. So we can explore the laws of physics under those extreme conditions. That's what Alice is particularly interested in. LHCb, the other special purpose experiment, is looking very carefully at the tiny differences between matter and antimatter. On an earlier slide I said they were like mirror images of each other, but actually they can't be exact mirror images because we somehow have to explain why the world is made of matter, and although we've looked very hard, we've found no evidence of antimatter in the universe. So there have to be tiny differences. We can measure these tiny differences. We can see the tiny differences. Anyway, we have 4 gigantic underground caverns to host these detectors. Because we're dealing with very high energies, we need very large detectors to absorb and measure all of the energy of the particles. We have the highest energy of any accelerator in the world. We have the most intense beams. And, although I don't have time to talk about it in detail, in order to guide the particles around in this big 27-kilometer ring, we need very, very strong magnetic fields. And to produce those magnetic fields, we have electromagnets carrying very high currents, up to 13,000 amperes. And if you wind a coil out of ordinary copper or aluminium and try to pass 13,000 amperes through it, it will just melt or even vaporize. We use a very special alloy of niobium and titanium, and if you cool it down to only just above absolute zero, 1.9 Kelvin, 1.9 degrees above absolute zero, it loses its resistance completely. It becomes a superconductor. And that means that it can carry these 13,000 amperes with absolutely no resistance and therefore no joule heating. So that means 1.9 Kelvin is actually colder than outer space. The temperature of outer space is 2.7 Kelvin, so we're nearly a degree colder than outer space. I like to say it's not just a world record low temperature, it's a galactic record low temperature. Unless perhaps there is a distant planet with little green people who have built themselves a Large Hadron Collider with even better parameters than our own. Can never exclude that. Okay, this is what the magnets look like. They're 15 meters long. They're actually double magnets. Most previous colliders have always collided particles with their antiparticles. So electrons with positrons, or at Fermilab, protons with antiprotons. Because clearly, if you have a positive particle moving from left to right, that's a positive current, but a negative particle moving from right to left is also a positive current. So a single vertical magnetic field will bend both of them round in the same circle. But here we're colliding positive protons, or lead nuclei, with positive protons, or lead nuclei. We actually need a magnetic field that goes up through one beam and down through the other to bend them both round. So all of these magnets are actually double magnets, two vacuum tubes here, vacuum pipes, 27 kilometers around the ring, carrying particles in one direction, and the other one carrying particles in the other direction. With the coils of this niobium titanium material. When you go to CERN, I'm sure you'll see these in some detail. That's what they look like underground, the long blue magnets to guide the particles. You can see over on the left-hand side the gentle curve of the tunnel, and then there are some shorter white magnets to focus the particles down. Remember, these bunches are only 16 microns in diameter. We squeeze them down so that we get more collisions. The more we can squeeze them down, the more collisions we get. It's like having two groups of people crossing a field. They're not going to bump into each other, but the same number of people in a very narrow tunnel, they'll bump into each other all the time. So the more we can squeeze our particles down, focus them, the more collisions we get for our fixed number of protons. Okay. Some statistics, well, I can come back if necessary to that. Just pick out a couple of them. The speed of our protons is 99.9999991% of the speed of light. They're actually going at about 2.5 meters per second, slower than light itself. The stored energy in each beam, 300 megajoules. That's equivalent to an express train. So you want to make sure that the beam stays in the vacuum pipe and doesn't stray away and damage the magnets. It's cooled by 700,000 liters of liquid helium at this very low temperature, 1.9 Kelvin. Liquid helium is quite expensive. Litre for litre, it costs about the same as whiskey. So we have the equivalent of 700,000 litres of whiskey. And we had to keep it cool because each litre of liquid helium, if you let it warm up, will become 700 litres of gas, and we have absolutely nowhere to store that amount of gas. So the most we can do is actually warm up 1/8 of the machine to work on it, cool it down, move round to the next one. And that's what's happening over these 2 years. We turned off the LHC in spring 2013, we'll turn it on again in spring next year, 2015, and we've been working around upgrading and maintaining the machine. Okay, so now moving on to the experiments. As I mentioned, there are 4 experiments. I spoke very briefly about ALICE, looking for the collisions between the lead nuclei. ALICE stands for A Large Ion Collider Experiment. And LHCb, looking for the differences between particles and antiparticles. These differences show up best by comparing the decays of particles containing the second heaviest quark, the B quark, bottom quark, with particles containing anti-B quarks. But the main detectors, what we call the general purpose detectors, are Atlas at the bottom right and CMS at the top left. We have to collect everything that comes out of the collisions because, as well as looking for Higgs bosons, we may have surprises. Nature may have surprises for us at these very high energies. So we have to catch all the particles that come out of the collisions, a hermetic detector. Now you might think the best way to do that is to make a spherical detector around the collision point, but actually it's easier to put together and to take apart for maintenance if you make it cylindrical. So you see the cylindrical shape of Atlas, cylindrical shape of CMS, with end caps in both cases, so that we do catch the particles that come out of both collisions as well. But actually that's where the similarity ends. We tried to make CMS as Atlas and Atlas as different as possible. Because if we built two identical experiments, we'd be wasting half of our money. But by making them as different as possible, we can check up on each other. The fact that the Higgs boson was seen separately in Atlas and CMS makes it more likely it was a real thing rather than some mistake in the design of the experiment. So the first big difference is in the direction of the magnetic field to bend the tracks of the particles and measure how fast they go, measure the momentum. In Atlas, there are 8 of these rectangular magnets, these long rectangular superconducting magnets, which produce a magnetic field that goes around the outside of the detector, rather like a hollow donut. And a fancy word for donut is torus. So Atlas stands for a toroidal LHC apparatus. CMS, on the other hand, has just a single magnet. You can see the grey coil there, circular coil. A fancy word for coil is solenoid. So the S of CMS stands for solenoid. I'm sure you all know that magnetic field lines never start or end. Electric field lines start on positive charges and end on negative charges, but there are no magnetic charges in nature, so magnetic field lines are always continuous curves. So the magnetic field starts off along the direction of the two colliding beams, but is then guided back by all that red stuff, which is 10,000 tons of iron, the yoke of the magnet, to guide the magnetic field back again. Now, CMS is actually, because of the weight of the iron, it's only half the size of Atlas. Looks the same on this picture, but you see a person to scale for Atlas here, and a person to scale for CMS. CMS is half the size, but twice the weight of Atlas, so the C of CMS stands for compact. The M stands for muons, because we're particularly good at detecting muons as the daughter particles. So compact muon solenoid and a toroidal LHC apparatus. So those are the detectors. What we have to do is we have to detect and measure all of the particles from the collision, this hermetic construction. How am I doing for time, by the way? Yeah, and what is it now? 5-2. I've got 5 minutes. Both of those detectors measure different properties at different points, so it's rather like a cylindrical onion. We measure, first of all, the direction and momentum of the charged particles in the magnetic field. Then we measure the energy separately for particles that interact electromagnetically. That means electrons, positrons, gamma rays, and the hadronic particles, the protons, the neutrons, ions, and neutrons. Then we detect the muons in the outer chamber. And then finally, missing energy. If a neutral particle, for example like a neutrino, goes right through the detector without interacting, which they do most of the time, we only know they're there if we add up all of the energy in every direction and find that there's an imbalance. If there's missing energy in one direction, we know that was carried away by a neutral particle. But what that means is, of course, every part of the detector has to be working all of the time, because if you had a dead region, that would look like a neutrino going through it. So that's CMS. Here's another view of the detector. The purple in the middle is measuring the tracks of the particles, the green measuring the energy of the electromagnetic particles, the blue, the hadronic particles. Then comes the coil of the magnet, and finally the iron with in slices with detectors interleaved with it to measure the tracks of the muons. This is what it looked like very early on in the construction. The grey thing is the container for our coil. It's also a superconducting magnet, so it's bathed in liquid helium, not at 1.9 Kelvin, but at 4.2 Kelvin. And then there are layers and layers of the iron threaded on, and you can see the gaps in the iron there, because that's where we're going to put the muon detectors later. All of the other parts of the detector sit inside the coil of the magnet. It's an enormous coil. It is actually the largest electromagnet in the world. It's into the Guinness Book of Records. And the iron, the total amount of iron is over 10,000 tons, and our French colleagues like to remind us that that's more than the Eiffel Tower. This is what it looked like just before it was closed. I don't know if the picture shows up very well, but on the right here is the cylindrical part. It extends over here about 30 meters. There will be one end cap on the right, and here you can see the end cap on the left, about to be pushed in to fill the hole there so that we do catch all of the particles coming out. And there's a chap on the floor there to give you the scale of the phone. So here are some typical events recorded in CMS. You see the tracks of the particles, they're curved. The more curved they are, the slower the particle is going. Some of you will know the relationship between the magnetic field, the momentum, and the radius of curvature of the sharp particle. And then the blue and the red Lego plots are the energy deposited in those two calorimeters. So by analysing that, we can reconstruct what happened in the tiny fraction of a second of the collision was a Higgs particle made, for example. One of the ways we do recognise a Higgs particle is if there are four muons, very high energy muons, so you can see they're very straight tracks, high momentum, and they're detected in the outer layers of the detector. But here's another example. This is a Higgs, maybe a Higgs, it's a candidate, which decays in the first step to two Z particles. Z particles are not quite as heavy as our heaviest particle, the top quark. Remember, the Higgs couples to mass. The heavier the particle, the more it couples to the Higgs. But unfortunately, the mass of the Higgs is not enough to make two top quarks, the heaviest quark. You need to make two because you've got to make a particle and an antiparticle to balance it. If they're matter particles, you don't have to do that if they're false particles. So the next heaviest particle is the Z particle, it's a false particle. You can make two of those, and they in turn decay either to produce two muons, one mu plus, one mu minus, or perhaps two electrons, E plus and E minus. So the way you would recognise them would be either with four muons, two from each Z, or four electrons, two from each Z, or in this case, two electrons and two muons. The green tracks, the straight tracks there, are the muons going right through the detector, and the little blue lumps here, top and bottom, represent the energy deposited by the electrons in the electromagnetic field. This is one that you might think wouldn't happen. Gammas have zero mass, so they're the lightest particles. But if the Higgs decays to heavy particles, which then radiate photons, and then the particle and the antiparticle recombine, so all of the energy can go into photons. That is actually a very nice way of recognizing a Higgs particle. Here's another two gamma. There's a lot of noise going on. You've made the Higgs particle by two, let's say two muons collide, but all the rest of the proton produces that fuzz in the middle. But how do we know that if it was a Higgs? There are other ways of making four muons, four electrons, two gamma rays, whatever it might be. It could be that two quarks collide and produce one photon, two other quarks collide and produce another photon. They've got nothing to do with each other. That's what we call the background. But we don't just identify the particles, we measure their directions, we measure their energy, so we can calculate what would have been the mass of the parent particle. And these background events can have any possible mass, they're just random events. But the Higgs particles will always have the same mass, the Higgs mass. I mentioned we have thousands of computers, 20,000 computers at CERN. other computers all around the world connected together, total of about 100,000. Here they are in the different countries. This is the final result. This is the plot. On the horizontal axis, it's what we call the effective mass, the mass you calculate from the direction and the energy of the two photons. It's actually easier to make a background event with a lower effective mass, 110 GeV, than a higher mass, so that's why the curve is falling all the way. The vertical axis is the number of times this happens. So it's mostly background, but as you can see, there is this little bump at about 125 times the mass of a proton. But you'll notice that the random background curve has fluctuations in it, as you'd expect if it's random. How do we know that that bump isn't just a bigger fluctuation? That was the situation we were in December 2011. We had a bump, but it only had a statistical significance of 3.5 standard deviations. A colleague of mine said that that's equivalent to being given a coin and asked whether it's biased, and you toss the coin and you get 8 heads in a row. So your suspicions are that it's biased, but it could be just random. But by the time we got to July 2012, we had enough events that we had 5 standard deviation significance. It's only 1 part in 10 million chance that that fluctuation, that should be just a large fluctuation. It's much, much more likely to be evidence for the Higgs. So by the same analogy, it's like tossing the coin and getting 20 heads in a row. It could still be random, but it would be very, very random. So we have a bump like that in the 2 photon, the 2 gamma decay, also in the muons and electrons, and so do Atlas. So we both published our papers together in the July 2012 issue, and that was the discovery. And so the people who proposed this, Englert and Higgs, but not Brock because, as I said, he's dead, got the Nobel Prize. This is the mass of the particle, 126 times the mass of the proton. But is it really the particle predicted by Peter Higgs? Could it be that nature was even cleverer than him, and our particle has different properties from the properties that were predicted? That's why we've got to go on now, when the NHC comes back on in 2015, and measure the properties in detail to see whether it is. And I write there, your chance to share in the discoveries at CERN. These experiments will go on for another 20, 25 years possibly. Perhaps continuing at CERN, perhaps at new accelerators at other places. Your chance to go to university with a physics degree, and then join a particle physics group for a PhD, and perhaps work alongside us at CERN. So I think, oh yes, we even have a t-shirt. We found a new particle. I think that really is the last time. Thanks for listening.